Let's explore limits as x goes to infinity with some examples. So let's start with the following. The limit as x approaches infinity of, and we're going to look at rational functions. So x to the fourth plus x cubed minus 1 all over x squared plus 3. Okay, what is this rational function going to as x goes to infinity? The way to look at problems like this is to look at what's the highest power? Is it in the numerator or the denominator? Now the highest power here is actually in the numerator, right? And what that means, if you look at a curve, okay, I don't know what this curve is going to do, but eventually the x to the fourth is going to dominate and it is going to shoot off to positive infinity. So when you have x going to infinity, if your highest polynomial power is in the numerator, it absolutely goes to infinity. Okay, next, let's take a look at the limit as x approaches infinity of x squared minus 2 over x cubed minus x. Okay, what does this limit go to as x goes to infinity? Okay, well, we've got the highest power in the denominator. And so if the highest power is in the denominator, in effect, what you have is some number over infinity, which then goes to 0. Okay, so if the highest power is in the numerator, it goes to infinity, denominator goes to 0. Now, can we justify this? I'm just telling it to you. And there is sort of a technique that works. What you can actually do, you can take, you can divide by the highest power of the denominator. Let me show you how that would work here. So if we do that, okay, we still have the same limit. And we're going to divide everything by x cubed. So we get x squared over x cubed minus 2 over x cubed. And then we've got x cubed over x cubed minus x over x cubed. And then this reduces to limit as x approaches infinity of, we've got 1 over x, we keep the 2 over x cubed, and then we've got 1 minus 1 over x squared. Now what you're able to do with limits is, it is a law of limits that if you have a rational expression, you can take the limit of the numerator and the limit of the denominator, and if you're looking within one of those, like the numerator, if you have the limit of a plus b, that is the limit of a plus the limit of b. So you can distribute the limit to each of these terms. Now when you do that, what happens? Clearly, if you have, we already did this one, if you have 1 over x, limit as x goes to infinity, that's 0. Likewise, 2 over infinity goes to 0. This is just 1, and this clearly equals 0. Okay, so this is some justification of the limit going to 0. Note that for this to work right, you have to divide by the highest power in the denominator. If you divide by the highest power in the numerator, like in this first one, you'll get like 1, I think, over, we get 1 over 0 maybe. It's not precise. If you just divide by the highest power in the denominator, it will work. Okay. So let's take a look at some other examples. How about the following? So we've got the limit as x approaches infinity of 2x squared minus 4 over, let's say, 3x squared minus x. What do we do here? Okay, this is interesting because now we don't have a higher power in the numerator or denominator. Okay, it's in both. And so now this technique of dividing by the highest power of the denominator is very valuable. So let's apply it and see what happens. Okay, so you bring down your limit. And now, I'm just going to go ahead and divide through, because if you divide every term by x squared, you get 2 minus 4 over x squared. And then you get 3 minus 1 over x. So as x goes to infinity, you can see the two terms on the right-hand side, in fact, do go to 0, and you're left with 2/3. And that is actually the correct answer. So the limit as x approaches infinity is 2/3. Okay? And so what you would have there is you would have a horizontal asymptote. Okay? So here's 2/3, say. And I don't know what happens, I'm not going to graph the whole function, but eventually, this will get closer and closer to 2/3. Okay? That's what it means. That is how you find horizontal asymptotes. You take the limit as x approaches infinity. Okay, and what do you get? Here you get 0. Okay? You can also try negative infinity on this. Okay, so this is really valuable. And so basically with this kind of a technique, you should be able to quickly get all the limits as x approaches infinity of polynomial equations. Let's do another one as an example. Limit as x approaches infinity of, let's go with 3x to the 4th plus x to the 3rd plus 1 over, how about negative x to the 4th minus x squared? Okay, what happens here? So the idea is to look at it like you did the top one. And what's going to happen is, like the x cubed term, the 1, and the negative x squared term will all go to 0 when you divide by x to the 4th. And so you will be left with simply, just like in the one above, a 3 in the numerator and a negative 1 in the denominator. And so if you can see that, you can see right out that this goes to negative 3. Okay? So this is the idea. This is how you can quickly get limits as x goes to infinity of polynomial expressions. We can maybe do one more. What if we have the limit as x approaches infinity, not of like a polynomial expression, but what if we have something like, how about e to the negative x? How do we tackle this? So what I would do is rewrite it as limit as x approaches infinity of 1 over e to the x. Okay? Why am I choosing to rewrite it like this? I think it's a little more clear because e to the x, okay, e to the x is an exponential function. It goes like this, right? As x goes to infinity, e to the x grows without bound. E to the x goes to infinity, okay? So we have a denominator going to infinity, and 1 over infinity, in effect, gives us 0. So the correct answer for this is 0. Note that, if we did x goes to negative infinity of this, okay, what would we get? U would be on the other side. And so e to the negative x is going to look something like this. It's the reverse, And so if it was going to negative infinity, it's actually growing without bound. Okay? And so you would, in fact, get infinity. Okay, so you've got to be careful when dealing with functions. And just to quickly review, whenever you have rational expressions, if the highest powers in the denominator as x goes to infinity goes to infinity. If the highest powers in the denominator and x goes to infinity goes to 0. And if they are equivalent, you must take into account the coefficients of the highest power, and it is simply the one coefficient over the other. So it's 2/3 for 3, it's negative 3 for 4. Okay? And if x goes to negative infinity, you must take the sign into account. Okay? You have to be careful about it. If you can think of it as like a positive negative, and I guess just to finish it out with maybe one more. What's the limit of x cubed as x goes to negative infinity? Okay, it's not the same thing as if it goes to positive infinity. In effect, you plug in a negative value, and when you cube it, you get a negative value. So this goes to negative infinity. So when it comes to positive and negative infinity, you must pay attention to signs and powers.